Hello, everyone. My name is Mandovi Mukherjee. I'm a third-year PhD student at Georgia Institute of Technology. I am from the Department of Electrical and Computer Engineering. Today, I will be presenting the paper that we submitted to IEEE Census 2020. So with that, I will go ahead with the presentation. Thank you. So like I mentioned, my name is Mandovi Mukherjee, and I will be presenting our paper, Algorithm Circuit Cross-Layer Control for Digital Pixel Image Sensors, submitted to IEEE Census 2020. The other authors of this paper are Burhan Ahmad Mudassar, Minah and Saibal Mukhopadhyay. I would like to thank all the authors for their contribution to the work. So the work that we have carried out in this paper focuses on utilizing cross-layer feedback originating from algorithm layer to control pixel depth of digital pixel circuit layer. So moving on to the outline of this presentation, I will first start off by describing the motivation and goal behind the work, followed by an overview of the proposed approach. After that, I will talk about some of the circuit techniques involved in the work. I will then go on to talk about the results and finally conclude the presentation with some of the future directions of the work. So in terms of motivation and goal, digital pixel cameras allow pixel parallel readout, or more specifically, the digital pixel circuits themselves allow pixel parallel readout. As a result, they show potential for very high frame rates and high resolution. As such, they're very attractive for application in IoT edge devices. And with 3D integration and feasibility of including a processing engine within the camera platform, in-sensor machine learning is a definite possibility. However, the active energy consumption of digital pixel circuits in such systems can increase significantly as we target such high frame rates. So this becomes an area of concern. Our goal in this work is to reduce the active energy consumption of the digital pixel circuits, the readout integrated circuits, or ROICs as we call them, without compromising the performance of end machine learning tasks. So here's a look at some of the prior work in this area. Authors have previously looked at feedback control mechanism within the camera platform, but within the algorithm layer. There have been papers which have looked at a task-oriented sensor-level feedback from an embedded processing unit. However, the granularity of control in that case was a window on the imager, and the main focus of the work was reduction in data transmission. So our focus in this work is to use cross-layer feedback from algorithm layer to control digital pixel circuit parameter, namely pixel depth in this case, to reduce active energy consumption. We propose a digital pixel capable of achieving multiple pixel depths under cross-layer digital feedback, and we do have potential for per pixel control. So going to the proposed approach of this work, this is an illustration to show how the full system works. So the DNN drives the feedback control. So there is an incoming frame, and from the frame, there is the response of the digital pixel, and the ROIs are detected, and then the predicted ROIs are fed back to the sensor level. So now for the subsequent frames, the sensor has this information of which pixel to maintain at what depth. So the ROIs are maintained at full depth, and the non-ROI regions, the pixels of the non-ROI regions, are controlled to operate at lower pixel depth. So this is what we show as a non-ROI pixel, and it shows a reduced response. So with this controlled response, we get lower active energy of the pixel that is under depth control. And this is how it flows. So the depth control is dependent on the pixel intensity and the pixel membership in an ROI or non-ROI region and the target depth. From a system point of view, the algorithm layer generates a feedback, but the control parameter is the pixel depth. The layer sends to the circuit layer information about ROI, non-ROI regions, the target pixel depth, and the digital control word based on the end task. And from the circuit perspective, it utilizes the digital feedback control word to set the pixel depth. So here's a look at some of the basic circuit techniques that we use to achieve the multiple pixel depths. We use a digital pixel that has been proposed in literature already, and we modify it to achieve depth control. The basic operating principle of this digital pixel is the generation of spikes as the capacitor at node FD discharges with the photocurrent. The number of spikes generated gives the pixel response. So by controlling the current at node FD with the help of a digitally controlled bleeder circuit, we can modulate the frequency of the spikes. And this in turn will modulate the frequency of the pixel response. Now, the active energy consumption of the pixel is directly proportional to the number of spikes, to the frequency of the spikes. So this reduces the active energy consumption of the pixels as we reduce the number of spikes. So once we have the circuit simulation, we would like to evaluate the results. So to do that, we have selected a case study so that we can evaluate the circuit results based on a case study. So what we do is we take the results from circuit simulation and we create the lookup tables or the LUTs. Now our case study is the DNN Object Detection. So given an input image, the circuit-based depth-controlled version of the image is generated by referring to the LUTs that we just created. The DNN algorithm generates the ROI information. Now the original image and the new image are merged based on the ROI information to create the image containing ROI and non-ROI regions. Now this is the image that is used to run object detection. A few details on the DNN side. We evaluate the pixel depth control with a case study as I just mentioned. The DNN object detection task runs on a sequence of input images and depth control is actually applied based on circuit data and ROI information in cross-layer feedback. For evaluation of the final results, we use a few metrics. PSNR is used to assess quality of generated images after depth control. And along with this, we use tracking accuracy to evaluate performance of object detection tasks. So we will now move on to the key results of the case study. So first of all, we have presented some sample videos with the frames which demonstrate the effect of depth control. So a few terminology, first of all, ideal pixel depth control or M-bit ideal pixel depth control refers to the case where 8 minus M lower order bits of a full 8-bit pixel response are set to 0. So given an input original sequence of frames, if we apply uniform ideal control to all the pixels, this is what the resulting sequence of frames looks like. So as we can see from the videos, there is a degradation in PSNR and we get the same results from our simulations. A few details on the DNN side, we have used SSD Mobile Edge version 1 and the Camel dataset as the input dataset with frame size of 336 by 256. So as I mentioned, the PSNR of the resulting images show degradation under the uniform control. So we go to the next part of the experiments. Now we take cross-layer pixel depth control. By cross-layer, I mean that the pixel value of the cross-layer pixel depth control refers to generating the pixel response with the LUTs from circuit simulation, as discussed in the co-simulation environment. We present the effect of cross-layer control on input frames in an ROI feedback mode, a region of interest-based feedback mode in this video. So as we can see, the PSNR values with the ROI feedback with cross-layer control for the region of interest regions are no longer degraded, and we get the same results from experiments. So keeping this in mind, we move on to evaluation of the object detection task. So we study the performance of the end task under ROI control. From the trend and accuracy results of the ideal control, we can get an indication of the fact that pixel depth control can be a valid form of control and it can maintain accuracy of the end task. So the tracking accuracy or MOTA, it shows minimal degradation under cross-layer control as compared to the ideal control. So these are the results that have been presented in this slide. And we have performed the case study with the tracking accuracy curve observation under both nominal and elevated temperature. So we move on to the energy analysis of the digital pixels. The results of energy obtained from circuit simulations are stored as LUTs, and these are the ones that are used in estimation. So we can see from the graph that the cross-layer control method achieves an energy savings of around 53% to 68% in ROI feedback mode, based on the target pixel depth used. So we can also see that if we go for uniform cross-layer feedback, we would get slightly reduced energy, that is a greater energy savings, but there is a substantial PSNR degradation, like we already observed. So we have further tried to present a projection of system-level energy savings. For this, we have actually considered an existing accelerator from literature with power of 3.2 milliwatts. The baseline power of our digital pixel circuit is 2.84 milliwatts. Thus, considering ROI-based cross-layer control, we project savings of around 25 to 30% based on the pixel depth. So I now come to the conclusion of the presentation. We have presented a task-dependent cross-layer methodology to control multiple pixel depth of image sensors. We have evaluated the performance of the cross-layer pixel depth by a case study which is an object detection task. And we have demonstrated significant active energy savings of digital pixels while maintaining accuracy of end tasks. So in terms of future directions of this work, design and analysis of full system considering all the components like sensors, ROIC, and accelerators, along with the intermediate data transfers would be an interesting area to look at. So with this, I conclude my presentation. Thank you.